Good morning, everyone. I'm Rohit, and today I will be talking about data lineage in Apache Beam. We will start off with some introduction and motivation behind data lineage. Then we will dive right into a demo where we will show a Beam job emitting asset level lineage, and we will visualize it with a GCP service called Dataplex. Then we will go into talking about how we build the data lineage support in Beam, how we use it in Dataflow. So data lineage is ability to trace the origin, transformation, and movement of data as it is being processed in a system. Data lineage can help us give insight into questions such as where did the data come from? How was it derived? How was it modified? How is it being stored? And what are the downstream dependencies which are actually consuming that data? There are four major classifications of data lineage. First one is asset level lineage, which tracks the relationship between one or two or more data sets or tables. Then there's column level lineage, which tracks the origin and transformations of columns. It's generally less granular, and it gives a broader picture of how the data was transformed. It's mostly used for impact analysis and schema management. Then there's row level lineage, which tracks the origin of and transformation of individual rows. And it's more granular, giving picture about how the exact each and every row was sourced. It's used mostly for data quality, compliance, and debugging purpose. Lastly, there's field level lineage, which is very similar to column level lineage, but the term field is used mostly in terms of unstructured or semi-structured data as JSON or XMLs, which are not as structures of a typical relational database where you have a full, very structured data of rows and columns. So lineage is important because by understanding the data's origin and transformation, it is easier to assess its accuracy, completeness, and reliability. This builds trust in data-driven insights and decision-making. Also, before making any changes to a data processing system, lineage can help us anticipate potential consequences and avoid any unintended disruptions to reports and application. It also helps us to do a root cause analysis. When an issue arises with data quality or any kind of inconsistencies, lineage can quickly pinpoint source of the actual problem and enable efficient remediations. It can also be used by many industries who have strict data governance and compliance requirements, such as GDPR, HIPAA, etc., to help demonstrate how data was handled, ensuring adherence to such strict guidelines. Lineage can also help track sensitive data and ensure proper access controls, and data maskings are applied throughout the life cycle of the data processing. So we will go into a demo. For a demo, we have a simple GCS to BigQuery pipeline, but this pipeline is dynamic in nature, as in it reads from a GCS bucket, and the file path which it's reading from has a wildcard pattern in it. So it's determined at the runtime how many files will end up matching with that wildcard pattern. So it's not fixed that it reads one or n number of files. Then the input, we are also providing the input file path through a command line, through an argument to the pipeline. And the file consists of basically two columns. First is a type, which basically states the type of the message. We can assume that it's a log messages, and it has types such as errors, want, info, etc. And then it's the message. And then lastly, we write the messages to a BigQuery dataset using dynamic destination. And we are choosing to use dynamic destination to demonstrate lineage to showcase the dynamic nature of our lineage tracking capabilities. So dynamic destination allows the table name where it's being written in BigQuery to be determined by some field or some value in the per record. So we will be showcasing how we are able to track the different tables which are being written to at per record level. Before we go into demo, I would like to briefly introduce to something called as Dataplex. It's a GCP service it's a GCP service which is used for visualizing and exploring lineage. And that's what we will be using to visualize the lineage today in this demo. So I have things set up here. Let me share this tab. So as I mentioned, we are reading from a GCS bucket, and we have a file path which consists of wildcard patterns. And there are two files which matches this. So this is my pipeline. And as you can see, I'm providing an input file. It has a wildcard pattern in it. And then in this bucket, I have two files which will match to it. I have already ran this pipeline. And this has read from the GCS from the files. But you can see that it's not known to the job, or we cannot find out by looking at the job graph itself how many files did it actually read and exactly which file paths were they. And similarly, we cannot find out by looking at the job graph. Let me share this tab. Okay, yeah. So as you can see, that's the wildcard pattern in the file path in the input file. Yeah, we cannot find out by looking at the job graph here that which files were read. Neither we can find out by looking at the sync node as which tables it was written to. So I have already ran this pipeline, and we can jump into BigQuery, and we can look at the tables here. So after the pipeline was run, dynamically, it created 3 tables based on the types of data. So my data consisted of log messages, which had type of error, info, and warn. So that's how these 3 tables get created. I can click on any of the table and try to visualize its lineage. So this is what I will end up seeing. I have that error table. It just shows the type and the message, which is the fields of that table. But the most important part here is this relation. So here we have this process. Ignore the icon. We are still integrating with Dataplex, so we don't have a fancy Dataflow icon yet in the UI. But if I click on here, I can see that this was a Dataflow job. It has a job name. It also shows me the different runs. So I only ran it once, but if I have run it more times, all the runs will come up here. I can click more, and I can see more details about the run here. When was it started? What was the state right now? For streaming jobs, it might be running for a longer time while the lineage is being tracked, the start time and the end time. But you can also see that you can visualize here that this BigQuery table was written by a Dataflow process, which actually read from 2 files, messages1 and messages2. So that's the lineage which we are talking about. And all of this dynamic reads and writes were captured by our lineage tracking capabilities, which we built into Beam. Okay, so that was the demo. So now we will talk about how we actually end up building lineage support in Beam at a high level. So before we actually build lineage, we have to consider the different kind of job graphs which Beam can have. As all of us know that Beam jobs are very dynamic in nature. It's a very developer-friendly platform to build pipelines. And developers can read and write from various sources and sinks. And these sources and sinks are not known pre-hand. It's only determined in most cases at runtime. For example, in this job of the dynamic destination case where we saw, this is the graph where you read from a source and then you have some transformations, and then you are writing to a BigQuery tables, but those tables can be n numbers, so you don't know how many tables the pipeline will write to. Then there's also dynamic reads, where it's not always necessary that the sources are at the root level of the graph. You might be reading from a pub subtopic, which consists of messages, which are actually the file path of the GCS file. You filter some of the file path, and then in middle of your pipeline, you actually end up reading the GCS file, which is right up here. Then the job, it's not necessary that the job will have only one sync or one sync is associated with only one source. So for example, here in case of multiple sources and sinks, you can see that this job graph represent that it's wrote to multiple sinks. Some sinks are created by reading from more than one sources. Some sinks are being created by reading from only one source. And then we also have side inputs, and it's possible to access some kind of resources inside inputs too. So we have to worry about that too. So at a high level, you can see that all of these job graphs are very dynamic, and the only way we can collect lineage is by doing it at runtime and doing it from the executor or the worker nodes. And to capture lineage, we also have to do it at per record level, because as we saw in the case of dynamic destinations, the tables or these resource locations which we are writing to or reading from can only be determined by looking at per record. And we have to do all of this lineage tracking without degrading the performance of the job or any of the IOs. So to do this, what we did was we built upon Beam's existing metric architecture. So just to give a brief overview of metrics in Beam, metrics in Beam gives visibility into the pipeline while it's running. It can be created dynamically, and it can be scoped to per step. So every step can choose to emit its own metric. And it has graceful degradation, which is something which we wanted while building Lineage, that if a runner does not support this, then the metrics will just be dropped, but the pipeline won't fail. So that's how it's being used in Lineage. If a runner does not support emitting Lineage or tracking Lineage, the pipeline will still run. It will just not capture the Lineage information. Currently, the supported types of metrics in Beam is counter, gauges, distribution, and histograms. Typically and traditionally, metrics are generally numerical in value, but they don't have to be. So we added a metric in Beam called string set, which, as the name suggests, is basically a set which contains all unique strings which has been reported. And IOs, or the transforms, can report the resource locations which they are reading and writing from using this string set metric. And this string set metric can also be used to capture all different kinds of information. For example, the schema of the record, or the type of the transformation which was performed, or any kind of JSON structure too. And lineage information via metric can easily be provided by any of the IOs. Any developer who is writing a new IO, they can emit that string set metrics and record the lineage, as in where sources and sinks they are reading or writing to. And then the system and the runners can consume it to build this lineage graph of data which is being read and written to. The runner don't, in this whole architecture, the runner don't need to inspect any of the IO to collect the lineage information. And this is generally approach which a lot of data processing system and a lot of services use to collect lineage. And it's very brittle because as the IO evolve, the IO might change, and this kind of visiting the IO to collect lineage information breaks. We also added a lineage class, which is basically a wrapper around the string set metrics. And we introduced a namespace called lineage, and it has two named metrics, sources and sinks. And these sources and sinks are the metrics which tracks the sources where the job is reading from and the sinks where the job is writing to. So to build upon this, emitting lineage from any of the Beam transforms or IOs are pretty easy. All you have to do is just do a lineage.get sources or get sinks, and then add the resource locations which you are reading or writing from. And it can be used as any of the metrics which are being used in Beam. And it can also be done in any custom IO which any developer writes. So once we have the metric, the lineage metric being reported from the Beam job, we need to build lineage graphs. So a lineage graph looks something like this. So for example, here you can see that there is this sink, and then there's this other sink too. And the lineage graph only represents that these sources were used to write to the sink. And then in the same case, the sources which were used to write to this sink. Here we have a dynamic read where the file source is in middle of the graph, job graph, but the lineage graph should also show that it was actually accessed and read from to create this sink. So once we have all this information from the job being emitted, the sources and sinks it's reading and writing, we actually need to build this lineage graph, which we are showing up here. And to build a lineage graph from the reported metrics, the individual step of which the reported metric which has been emitted by individual step, we first traverse the job graph, collecting all the paths from the sinks to the connected sources. I would like to highlight that just collecting the sources at the root level, as we saw in this graph, is not enough, because the intermediate nodes in the graph can also act as a source, and that's the file source which is here. Also, a single step can report multiple resource location, which is it's writing to. That's the case of BigQuery dynamic destination or any IO with supports dynamic destinations, where the same step can be writing to multiple data sets or multiple files, and we need to capture each and every data set it wrote to or file it wrote to. Lineage graph can also change through the life of the pipeline. So when a pipeline is running, it might happen that towards the very end of its life, it actually ended up writing to a completely new data set. So just capturing a snapshot of lineage information in a point of time is not enough. We have to keep capturing it across its life and building the lineage graph, recalculating it, finding if there has been any changes or not, and then report it to a lineage visualization tool. In the demo which we saw, the lineage visualization tool there was Dataplex. So currently in Beam, what we have added is we have added support for tracking asset level lineage and a couple of IOs, and we use that on Dataflow to capture all the lineage and report it to Dataplex. It's also possible to build upon the existing architecture and support column level lineage, where the individual transforms can emit the input schema and the output schema of the transformation and the operation which they have performed. And this can be done by a standard format, which is provided by OpenLineage. OpenLineage is an open source project focused on lineage collection. And basically, it just gives a standard format, which is a JSON representation of capturing and emitting lineage. And then that standard format is understood by different kind of visualization tools such as Colibra, etc. Once we have this, where the transforms are also emitting, like the transforms in the middle, not just the sources and sinks IOs, are emitting some informations, and the transforms are also emitting, we can again then traverse the graph and find out all the transformations in the path and collect that lineage and build a lineage graph as we are doing for the asset level lineage. And that's how we can support column level lineage in Beam. So currently for lineage, what we have is we have support for asset level lineage, which we have added to Java and Python SDK so far. We are working on adding it in Go SDK. We have supported IOs which emit asset level lineage information out of the box. The support is there right now as of now in PubSub, BigQuery, GCS, Cloud Bigtable, Kafka, and we are also working on adding to a few more IOs. As we saw in demo, that the lineage metrics which are being emitted by the Beam jobs is consumed by Dataflow, and it's being reported to Dataplex for visualization. But it's also possible for other runners, such as Flink, to use that Beam lineage information and visualize the lineage which is being reported by Beam. And to do this, all the runner has to do is support the string set metric. And by supporting, I mean that they should be able to understand the string set being emitted and be able to aggregate it as a set. And then build the lineage graph links, which is basically traversing the job graph and finding out all the sources in the path, and then reporting it to some kind of visualization tool which exists out there, such as Colibra or Marquez or something. Our future plans for Beam is to support column level lineage in transforms. And then after we have built that support where the transforms can emit column level lineage information, we want to build on top of that and provide out of box column level lineage tracking in Beam YAML. So once we have all of this lineage information from Beam, we are using that in Dataflow as of now. We have an upcoming launch for asset level lineage tracking. It will be supported for batch jobs, streaming jobs, templates, data pipelines, runner V2, pretty much every kind of job which exists. And to use it, all you have to do is update to the latest Beam SDK, which is released at that point, and enable lineage tracking by providing a service option. There will also be a UI checkbox to enable this, which is basically enable lineage. That's it for the presentation.